if there's any questions on anything we've been doing so far.
Yep. So you described 2 steps of the Chirac-Zollner gate last time. And the first step was moving the excitation from the electron state to the phonon mode. And in the but in that case, it went from E0 to EG1.
Yeah.
And
right.
then in the second step, basically at the end, we got a minus sign for the E1 state.
Right, but remember, it's now the E on the second atom. The first one was the E on the first atom.
Exactly. Okay. So and you were saying the third.
The third step is just to undo the first step. So you're transferring it from the phonon back to the atom.
So that basically the net effect is.
Well, okay. So
these are 3 different operations, or are they supposed to be
in sequence?
Okay.
In sequence. So it's. Let me just draw a little picture here. So we have.
Sorry. Yes. 8.
I'll do it over here. So we have. Atom 1, atom 2, and our phonon. And so the first thing to do is to move the information from atom 1 into the phonon. And then we do some sign gate between these 2 things. And then we move the information back, right? And so clearly the effect of this is to do this controlled sign gate. If you look at the whole thing as a unit, to do a controlled sign gate between the 2 atoms, which is what we wanted. OK? Does that make sense, Sal?
Right. The control sign.
Yeah. So it's the gate was basically this matrix 1, 1, 1, minus 1. OK. Any other questions? OK. So there was one more thing I wanted to tell you about ion traps, which is, so I talked to you about 1-qubit gates and 2-qubit gates. But that was in kind of the simplified model where we just had an ion trap with only 2 qubits in it. And well, of course, the same technique. I mean, if you can shine a laser individually on the atoms, will work if you have an ion trap with more in it. It's a bit difficult and is not going to work very well if you try to put your whole computer in a single trap. And the reason for that is that if you try to put, I mean, you can certainly put many more than 2 ions in a trap. You can put 30, 40. People have done tens of ions, definitely, in a single trap. But the thing is that when you do that, there's kind of a trade-off that you face. So one option is to weaken the trap potential and make the trap bigger. So the ions will have kind of the same amount of space between them, no matter how, well, as you put more and more, you weaken the trap potential, so the ions keep the same distance apart. Okay? But the problem is that that lowers kind of the energy scale of the phonon, and the energy levels kind of collapse together, and there's many, many modes, and they are also kind of getting close together. And so it's hard to talk to individual modes and excite individual excitations of the phonon mode that you want. And so obviously that's going to be a problem when you start to do 2-qubit gates. You can start to get errors from extra modes interacting or having too many phonons or stuff like that. But the other option is also undesirable, which is to keep the trap potential the same but crowd more ions into the same space. That means the ions will get closer and closer together. And among other things, it becomes, there's strong interactions between them. And when you shine a laser on one of them, because the ions are so close together, it's probably going to splash over to the nearby ions. And that'll cause some errors as well, because when you do a gate on one, you don't want stuff to happen to the other ones. On the other hand, one advantage of the ion trap, which is not going to be true of superconductors that we'll talk about today, is that you can do gates between qubits that are any 2 qubits, really, right? Because they're all interacting with the same phonon mode. So it is reasonable to have a number of ions in the same trap, but there's a limit. And exactly what that is one of these trade-offs that experimentalists have to deal with when they're designing a system. So there's kind of two main techniques that have been proposed for going beyond the limit of a single trap with ion traps. And aspects of these, really, these techniques have been demonstrated, but none of them is kind of fully mastered at this point. And that's one of the main barriers at the moment, I think, to scaling up the ion traps to large size. So one of them is to simply physically move the ions around. So for instance, you might have a situation like this. And there'll be a more complicated magnetic trap. And so you have a bunch of ions on the side here. And you can use lasers to grab an ion and move it around. And so you might say, OK, I'm going to push all these ions up, and I'm going to move this one into this intermediate section here. And I'm going to move these ones down and move this one into here. And then these two are close together. There's a phonon mode in this direction. And so we can do a 2-qubit gate in this section. This is kind of our gate region of our computer. And then when we're done doing that gate, we can move everything back to where it started and move 2 more atoms in there in order to do another gate. Okay. And of course, you can have much more complicated layouts than this, where you have many different regions and many different interaction areas and stuff like that. So that's one option. Obviously, whenever you're trying to move an atom around like that, there's a risk of introducing errors into its state. And so that's a drawback of that approach. So the other thing is that you kind of lose a bit of this this element of having things close together, right? Because if you have some big system like this, and even if you have lots of interaction areas, but you want to interact in an atom that's way up here with one that's way down here, you'll have to move them pretty far in order to get them close enough to interact with each other. Or you'll have to use some intermediaries. And that means that there is a cost to having long-range gates that you didn't have in the single trap example. So another approach is to put your ion traps in optical cavities. And so an optical cavity will have mirrors here. So this even doing this actually is a big advantage already, because instead of using a bus that's the phonon mode, you can instead use the optical mode in the cavity. So an optical cavity is a thing that has mirrors here to keep light inside for many, many, many round trips. You can make optical cavities with Qs. I don't know what the numbers are, but like 1 million or something. It means you can bounce back and forth 1 million times before getting out. You don't quite want to do it that high in this particular case, because the main reason to do this is that you want it to occasionally come out. But we want it to come out one end and not the other. So one mirror is going to be very, very good, and the other one is just going to be pretty good. And when it comes out, we're going to try to catch it into an optical fiber. And then we have these 2 cavities. And we're going to have these 2 beams of light. Well, not beams, because each of them is at best a single photon, and probably not that, because the light doesn't come out very often. And we're going to have a beam splitter here and 2 detectors. And suppose that we have a single photon in here and a single photon in here. And we do this. And then suddenly we see a click in this detector. What does that mean? Well, because we did a beam splitter here, we don't know whether it came from this cavity and then bounced up, or if it came from this cavity and went through. Right? And that's a coherent possibility. Each of those possibilities is coherent with each other. If you have the click down here, it's the same 2 possibilities, but the phase is different. The relative phase is different. And so what that means is that now what we have, now that we've seen this click up here, what we have is a superposition of a photon up here and a photon down here. That's an EPR pair. Okay? And then we can use quantum teleportation to move, and the atoms will interact with the photon in the cavity. And so we can use quantum teleportation to move a qubit from one cavity to the other. The atom stays put, obviously, but we're moving the information from a qubit, from an atom in one cavity to an atom in the other. Okay? And then we can do a gate using, the phonon or photon mode here. And actually, there's shortcuts, because you can convert an EPR pair directly into a gate with just some additional local operations without having to teleport it from one place to another. But it's the basic idea. Okay? So the problems with this, of course, is that this process of trying to get the light out and steering it towards this beam splitter is fairly unreliable and lossy and slow. So again, I think this has been demonstrated, but kind of scaling it up into a reliable procedure is a bit tricky. But the other advantage of this is that once you get it working, then you really can do long-range gates, right? Because moving the photons around across your computer is not that big a deal. You just have some optical fiber. And you can create entangled pairs at long distances and without too much effort. But yeah, so that's the kind of the current state of the art. And people are certainly continuing to work on ion-trap quantum computers today, although I think superconductors have maybe pulled ahead. Ion-trap quantum computers, I couldn't find an accurate number for the kind of the maximum size that people have really done full control on, but let's say around 20 qubits, certainly at least in the teens, and with quite high accuracies. So just to give you an idea, the timescales that we're talking about here, the heating of the phonon mode is kind of frequently the limiting factor in decoherence, and that's a timescale of milliseconds or tens of milliseconds. And error rates have, in some cases, been shown as low as 10 to the minus 3 for the 2-qubit gate, and lower for the 1-qubit gates. So that's quite good. OK? So there are questions on ion traps. Actually, there was one more thing I wanted to say about ion traps, which is if you go to an ion trap lab, the usual ion traps are kind of big things with a vacuum chamber and a lot of lasers sticking in and stuff like that. But people have also been building micro traps that fit on a chip, and they probably still have a lot of lasers and big thing around it. But the quantum computing part of it, the hardware is now capable of putting it in quite small area. Yeah.
So when you observe one of the photons, it doesn't. The entanglement doesn't collapse or anything, right?
That's right. So because just observing a photon here doesn't tell you where it came from.
Sure.
Now, obviously, there's other stuff that could happen. It could be that the photon didn't come from either place. It's a dark count. It's not a real photon. It's just a photodetector acting up. It could be that there's some, decoherence that happened somewhere else. So there's all sorts of other things that can happen. But in the basic situation, it does create an EPR pair. OK? OK. So let's move on to superconducting qubits. Maybe get a fresh board for that. Okay, so so ion traps are, in some sense, kind of simple. The experimentalists, they have to make a choice of what ion they want to use. They have to make a choice of what trap they want to use. And then there's a couple of different choices for how they want to do the gates and pulse shaping and stuff like that. But those are kind of relatively low-level details. So superconducting qubits have a much wider variety, and many more different types of superconducting qubits have been made. And there's no way I can go through all of them. I don't know all of them. I couldn't attempt to describe them all. But I'm going to try to describe some of the main elements that show up in these things and some of the more popular choices. So, so the main thing about superconductors is that, well, there's a couple of main things. So one of them is that, of course, superconductors are electrical in base, in nature, right? So we're talking about electrical circuits, fundamentally. And so it's going to use all of these circuit identities and circuit properties that you probably learned at some point, of capacitors and inductors. Not resistors, because they're superconductors, of course. Resistance is 0. And that has the advantage that you have the whole machinery of electrical engineering to draw on, both to kind of manipulate them and to hook them up and stuff like that. So the other important thing about superconductors is that whereas in the case of the ion trap, our qubit was basically the state of a single electron. In superconductors, the things that go are Cooper pairs, right? Pairs of electrons. But moreover, they form some Bose condensate, basically, and they have some collective motion. So it's not single Cooper pairs that we're talking about, but many, many Cooper pairs, like thousands or millions of them. And the reason we can still do that and still have quantum coherence is because of the Bose condensate acts symmetrically among all the Cooper pairs. And what that means is that the center of mass mode of these Cooper pairs kind of decouples from the other modes. And that's the only thing that we really care about. And so everything is going to be done with kind of the average of the movement of the Cooper pairs. And that thing is relatively well isolated from the environment, which is why we can kind of do things and still have a reasonable amount of coherence. Now, the coherence is still going to be much, much less in absolute terms than you see in an ion trap, whereas dephasing times for an ion traps can be seconds or longer, and even with the photon heating, remember that was milliseconds or tens of milliseconds. In superconductors, decoherence rates tend to be microseconds or tens of microseconds. Okay, but because electronic things operate at a very fast speed, you can do gates in tens of nanoseconds instead of tens of microseconds. So you can still get kind of similar ratios of decoherence time to gate time. And so you can hope for error rates of 10 to the minus 3 or lower. It's not quite as clean a system as ion traps, but it still works pretty well. And the best gates that have been done today are maybe a few times 10 to the minus 3, I think, for 2-qubit gates. Most of them are more on the order of 1%, though. This is maybe a good point to make a good time to make a point that if you look in the literature, experimentalists will say, well, OK, we'll work very hard and try to get the best possible gate we can, and they'll do that. But then they also work very hard to try to get many, many qubits. And frequently, these two things are in tension, right? So you can kind of optimize your 2-qubit system as much as you can to get the best possible gate. But then when you add more qubits, well, there's all sorts of other stuff that can happen. You can have qubits talking to each other that you don't want to be talking to each other. You have to put in more control elements and all this stuff, and it tends to ruin the optimizations you did for 2 qubits. So it's kind of rare that you'll see, oh, this is the best gate fidelity in this system. This is the best number of qubits. It's rare that you'll see that in the same paper. But they do both give you extremes give you an idea of what you can hope to achieve in that system. OK, so yeah, and so superconducting qubits, as I said, have kind of pulled ahead in some sense of the ion trap, certainly in terms of number of qubits. And that's one of the big advantages of superconducting is that because they're a solid state thing, there's a big industry devoted to manufacturing solid state. Most of that is in silicon, of course. But if I have time, I'll mention about silicon-based things later. But nevertheless, you can manufacture stuff much more large scale than for the ion traps, which is a much more different technology. And so the biggest quantum computer that I know of today is Google's experimental device, which is 72 qubits. I'm not sure it's actually done any kind of quantum computations yet. As of last summer, they had to kind of individually tune every one of these 72 qubits, and that takes a while. So I don't know what the current status of that is. But that kind of there's other groups that have 20. I mean, online you can access through web interfaces IBM's and Righetti's quantum computers with roughly 20 qubits. OK, so like I said, all of these superconducting quantum computers work by using circuit stuff. And so you can get some equivalent circuit to whatever they're doing that boils down to this. And then maybe something like this with so the X. This is a capacitor. Hopefully you remember that. This is an inductor. You might remember that as well. This one might not look so familiar. This particular thing is a Cooper pair box, and the X's are Josephson junctions. Okay, and the Josephson junction is kind of the key superconductor thing that lets you do interesting stuff. OK, so if you have a circuit that's like this, or I mean, really, the real things, of course, have more capacitors and more inductors, and maybe or maybe not more Josephson junctions. But using kind of those undergraduate circuit identities, you can combine inductors in parallel or sequence into one like this. Okay, and so the Hamiltonian that you'll get is of this form. So if you didn't have this thing, that would be what you get from an LC circuit. And that would be a harmonic oscillator. Now, because we're dealing with superconductors in kind of the mesoscopic limit, where, as I said, we can still have this center of mass mode that's fairly quantum, n and phi are going to be quantum operators. And they're going to be conjugate variables. So n is going to be the number of Cooper pairs on the capacitor. And phi is the superconducting quantum phase. Okay, the relative phase around, say, a loop here. Yeah, I'm not sure whether it's going to be between here and here, or let's say that. Okay, so then without this term, if we did it with superconductors, you'd have an actual quantum harmonic oscillator. But then adding this term, this is what's coming from the Josephson junctions. And Josephson junction acts like a nonlinear inductor. And that makes this whole thing much more interesting. So basically, this is going to turn it into some kind of anharmonic oscillator. And that lets us pick out individual energy levels that we want and do stuff with them. So the behavior of this system, and people have made a wide variety, as I said, of superconducting qubits with different kinds of parameters here. And as you change the parameters, the behavior of the system changes pretty radically. and the properties of it change pretty radically. And so people have basically tried making superconducting qubits in all sorts of different regimes of these parameters. So let's see what happens. So this term is kind of, in some sense, the least important, and it tends to be smaller, I think. So the main thing is to look at is the ratio of EC and EJ. So if you have EJ over EC small, then you're at one end. Let's see. And EJ over EC large at the other end. And large could be hundreds or thousands, I think. And small is, say, 1. So let's do this one first, actually. So what I'm going to plot is energy levels versus n sub g. And so in this limit, where EJ is very, very big, this term is going to dominate. And what that means is that phi, the phase, is going to want to sit at some particular value that minimizes this term, which I guess is like phi equals 0, something like that. OK? Does that make sense? So that means that phi is going to have a fairly concrete value and is maybe going to oscillate a little bit about that value. And so what that means is that you can probably expand cos phi using a power series around that minimum value. And that will kind of capture the important physics. And so what that means is cos phi is going to be like 1 minus phi squared over 2, right? And that phi squared over 2, that means that, and so if you make that substitution, that means that this whole thing goes back to being a harmonic oscillator. Okay. Now you still have some extra control capability because you can fiddle with these Gottesman junctions, but basically it's going to be a harmonic oscillator. And so the energy levels, and moreover, this term is negligible, so it's not going to depend. The energy is not going to depend very much on Ng. And so the energy levels are going to look fairly flat and evenly spaced, right? Yeah.
So what is NG?
NG is some parameter in here which is let's see, what did I write down exactly? No, it's just something that comes out of the exact design of the circuit,
So
but it's not an operator, it's a number, and the important thing is that, and the reason, well, okay, the thing that's going to help decide where we want to be on this diagram is that Ng kind of depends on the ambient charges in the system. So if you have some additional charges that are sitting nearby, then that can alter Ng. Okay? And so that's the advantage of being on this end, which is that you can't necessarily control very well what's happening around your system. There might be some additional charges floating around. This is a solid state system, not as clean as the ion trap. And so there tend to be extra stuff that you didn't, imperfections in your system that you didn't control. And so that means you can move back and forth, but at least in this case, you won't have a significant change in the energy. Okay? But the disadvantage is that because these are evenly spaced, this is a harmonic oscillator, that you won't be able to pick out a single transition to deal with. Let's see, I guess I didn't really want. OK, I'll leave it like that. So now at the other end, with the same axes here, it's going to look very bumpy. So what's going to happen is that this term is more important, or maybe dominating. And so n might have a very concrete value in order to be at the minimum of this potential. I mean, we're not going all the way to this being much bigger than this. But if we were, then n would have a concrete value, and we'd just sit at the bottom of that. But that means that we have to keep this whole cos phi, right? Because phi could be anything when n is not just anything, it's everything in some sense, right? It's a conjugate quantum variable. So it's completely spread out. So we have to worry about the whole cos phi. And so that means that it'll be very anharmonic. And if you actually solve for the case where they're kind of similar, the energy levels look something like this. So we have the lowest one is maybe some bumps like this, and the next one looks a bit like this, and then the next one is like this. So is that even right? Sorry. This bottom one is supposed to have its maximums at the minimums of the second one. There we go. So in this case, you can see that, first of all, that the difference in energy levels can be quite large. But moreover, the energy levels change a lot when ng changes. And one way to kind of ameliorate this problem is to try to sit at one of these points here, which is a minimum of the second level and a maximum of the first level. Because then when you get a change in ng, the change in the energy levels is a second order change. Okay? And then you can do, these are going to be your qubit, a ground state, and excited state. And you can pick out this transition very well from this next transition. It's a totally different energy difference. But you're very susceptible to charge noise. And so down here, this is called the charge qubit. Because basically what this boils down to is saying that your qubit is stored in whether you have, say, an extra qubit pair here or here. And that's the difference between the 0 and the 1, roughly speaking. And over here in the range where this is very large, this is called the flux qubit, because the thing that determines the value of the qubit is kind of more about the superconducting phase. And that's controlled by the flux, the magnetic flux, through, say, this little Cooper pair box. Okay? But then you get an intermediate regime where it kind of goes between these two. So you'll get stuff that looks like this. So maybe the bottom level will become more flat. The second level also becomes more flat, although it's still a bit bumpy. And then the one above is still fairly bumpy. And as you go further and further, you might get something like this. Okay, and so you see, as you make this transition, you're going from the case where it's very sensitive to charge noise to not sensitive, but also going from where it's very anharmonic to very harmonic. And so the approach that's kind of won out is maybe somewhere in here, which is called the Transmon, and variations of it, which makes this compromise between it's not the extremely large limit here or the extremely small limit. It's somewhere in between where the sensitivity to charge noise is pretty small, but you still have at least some anharmonicity. But it's not perfect anharmonicity, which means that you do have to worry a little bit about exciting the wrong level at some time. OK? So are there questions about this picture, these pictures?
So these are just one qubits, right?
Yeah, this is a single qubit. And so the basic model for superconductor is that we'll have some little circuit like this for each qubit, and then we have to couple them together somehow. And the point is that adding kind of more circuitry is not that big a deal. It's actually adding kind of the control stuff that starts to become the biggest problem. But are there questions about how this part works? Again, single qubit here. OK, yeah.
I was wondering, how do we excite from the ground state to the excited state? Do we use magnetic fields?
Yeah, so that's what I was going to talk about next. So how do you do gates, right? That's what that is, going from ground to excited. So this is just a question of kind of what this is. Remember, I didn't write up again the DiVincenzo criteria, but remember the first one was that we should have scalable, well-characterized qubits. And so scalable, yes, we can make lots of these circuits. Well-characterized, well, that's kind of this whole business of where to, I mean, charge noise is not the only thing you have to worry about, but it is a big thing. And so, knowing this energy difference is a big part of that. So that was kind of the first DiVincenzo criteria. But we also had to do, state preparation and gates and measurements, and we're doing this all in a context of trying to keep the decoherence rate low. OK, so how do we do gates? So one option, and again, and this is, so even once you kind of fix this parameter ratio that you want to work in and say, oh, we're going to do something transmon-like, there's still a huge variety of things that people have done, as far as I can tell. Every group seems to have a different design and do their gates differently. So there's kind of some big toolbox of tricks, and they again have to pick some trade-offs of which advantages and which disadvantages they want out of it. So I'm gonna kind of give a couple of examples and to give you an idea of the sorts of options that are available. So one thing you can do. So if you have this sort of structure that I drew before, you can inject some magnetic flux in here. OK? And what does that do? What does that do that changes the phase relation in this superconductor? Right? The phase has to, around the circle, if you don't have any magnetic flux, it has to match. It has to get back to where it started. But when there's magnetic flux inside, it has to go by some multiple of the magnetic flux. And what that means is that by doing this, you can tweak the energy levels and change, because you're adjusting this term, and change the energy splitting, the frequency of the qubit. So why would we want to do that? Well, one thing that lets us do is it immediately lets us do phase gates. Remember, because if the ground and the excited states have different energy levels, then as we wait over time, one of them will accumulate a phase relative to the other. And if we selectively, on one qubit, change that energy splitting, then that qubit will acquire relative phase faster or slower than all the other qubits. Okay? So whatever we're doing in our clock to keep track of this phase difference will be fine for the qubits that we didn't do this, but it will be off for the one where it did change. Which in this case is good because we're doing it deliberately in order to change the relative phase of 0 versus 1 for that qubit. Does that make sense? But of course, when it happens, when we don't want it to happen, then it's a source of error. And so having magnetic field noise in here is going to be a source of phase errors. OK? So the other thing that we can do with this is we can use this to put our qubit transition in and out of resonance with something else. Okay? And that's another very useful trick, because the next thing we'd like to do, another thing that happens is sometimes they'll embed these superconducting circuits in a microwave resonator, because the energy scales that we're talking about are usually microwave type frequencies. And even if you don't embed it, you might, to link it through a capacitor or something like that to a microwave resonator. So somehow we're going to couple this system to a microwave cavity that has a photon mode in the microwave. And the Hamiltonian we get out of this, well, it's complicated, but let's simplify down to something that looks like this. So this is the photon. The A's are the photon annihilation creation operators. So this is the photon Hamiltonian. And we have the qubit Hamiltonian. And then we have a coupling term. So here, sigma plus minus is sigma x plus or minus I sigma y. And these are kind of the raising and lowering operators for the qubit. So, I mean, through most of the course, I'm going to write the Paulis as x, y, and z. Here, I guess I followed the kind of more standard physics convention of sigma x, sigma y, sigma z, because, I don't know, this is experimental areas. It's more likely to do that. Also, I needed the plus and minus things, which don't so naturally work with the x and the y. OK, so this Hamiltonian is basically the same one as we had for the ion trap, with the atom coupling to the phonon mode. But there's kind of practical differences for how we're going to use it. And the first one is that we don't have direct control over this G, usually, except to the extent that we tune the qubit in or out of resonance with the cavity. Right? If these two frequencies are the same, then that's in resonance, and you get a strong coupling. When you tune it out, you'll get a weaker coupling. But of course, doing that also means that you're changing these frequencies and changing the way they process. So you have to be a little careful with that. But another way you can use it, and again, this is kind of part of the spectrum of different things that people do, is to just leave it fixed, and you'll have some fixed coupling between the atom and the cavity, or sorry, the superconducting circuit and the cavity. And that means that the actual energy levels that you're dealing with are no longer energy levels just of the superconducting circuit. They're joint energy levels of these two systems. And if this is a strong coupling, then they're not even close to things that are just on the qubit. They're much more complicated things. Yeah. And so the other difference, of course, is that the types of parameters, the kind of the size, relative sizes of these different parameters, tends to be rather different in the superconducting circuit regime than in the atom regime. Okay. I should say this is called the Jaynes-Cumming Hamiltonian. It's a pretty common one that you'll see. OK? So any questions on this? OK, so once we have this cavity, there's now become lots more options for control. So one option, I mean, because we can couple this cavity to other types of microwave circuits, we can like flood it with microwaves, and make the cavity to be basically a classical state inside it, right? The photon state. And so that means that we should no longer be using these A's and A daggers. because it's more of a classical thing. We'll be using the classical electric field and magnetic field. The thing is that if you're in this relatively strong coupling limit, where the superconducting circuit and the cavity are interacting very strongly, if the cavity becomes classical, the circuit is going to become classical also, right? And it's going to decohere. And so and that's bad, obviously, if you want to preserve coherence, but it's exactly what you want to do in order to make a measurement. So that's how you can make a measurement. And you can use it, once you make a measurement, you can then control it and reset. So that's also a way to do state preparation if you want. Anything decohering tends to allow you to do state preparation. Yeah?
So then how do you isolate from your qubits from microwaves? Because like the microwaves are everywhere.
Oh, well, yeah. I mean, obviously you need shielding. And remember, these are superconductors. So they have to be done at very cold temperatures. It's inside some dilution refrigerator. There's all sorts of stuff around them. Yeah, I guess I don't know, but I haven't heard that that's a significant problem in these systems. There's other stuff. It's a two-level system, stuff like that. That's a bigger problem. OK. So the other thing you can do is you can inject not a really strong microwaves, but much weaker microwaves. And again, it depends on kind of what your coupling strength is here. But that lets you, kind of do some deliberate A and A daggers, which then causes the circuit, the superconducting circuit part, to transition from ground to excited. And that lets you do your X and Y gates. So there's weaker pulses. OK? So for 2-qubit gates, again, you have various options. So one of those options is to use a cavity like this that's coupled not to just one superconducting circuit, but to 2, 3, 4, 5, some number of them. And then that you do something that's more like what we did in the ion trap, where we're using the cavity mode, in this case a microwave photon mode, as a bus to connect different superconducting qubits. Okay. Another option is to use your superconducting wires and circuits to make a capacitor that's just connecting. You'd have two things that look like that, and you add some extra wires with a capacitor between them. And now you have a coupling between these two qubits. But again, you want to, but this is a gate that you want to turn on or off, so you want some way of controlling that. Either you're tuning the frequencies so that they don't interact, or you're cutting off that coupling somehow. Again, there's variations, and I'm not really sure what exactly the considerations are there. But when you do that, you get a coupling that looks like this. So this term will kind of move the first one from 0 to 1, but this one down from 1 to 0. And this one does the opposite. And so what that means is that if you have 0, 0, or 1, 1 in these two qubits, nothing is happening. Or at least this term doesn't interact with them. But if you have 1, 0, or 0, 1, this will tend to switch them, right? 1, 0 can go, the 1 can go down to 0, and but only at the same time as the 0 goes up to 1. So this is called an exchange coupling. And you can see the same kind of coupling in a lot of other systems as well. So the thing is that if you run this for a certain amount of time, what it will do is it'll just switch the 2 qubits, right? Because 0, 0 to 0, 0, that's the same. 1, 1 to 1, 1, that's the same. But 0, 1 becoming 1, 0, that means I've really switched them, right? So what this Hamiltonian does is it generates the swap operation between these 2 qubits. But the thing is, you run it for a different amount of time, it will do something else. And it's something like, for instance, if you do it for half the time for a swap, you'll get the square root of swap. Which, seems nonsensical from a classical point of view, but makes total sense from a quantum point of view. And this is what the square root of swap looks like as a matrix. So the outside, the 0, 0 and the 1, 1, nothing happens, remember. So it's all happening in this 0, 1, 1, 0 space, and we get this. 1 minus I1. Okay? And it turns out that if you have this gate plus single qubit gates, that's a universal set of gates. Okay? And of course, you don't have just this gate, but you have, you could run this Hamiltonian for any amount of time if you have control to switch it on and off. Okay? And so that gives you one way to complete the universal set of gates, which was and so we had measurement, we had state preparation using the same techniques, and we have now a universal set of gates. And so that completes the DiVincenzo criteria for the system. OK? So there are questions on that stuff. OK, so then for the last 7 minutes, I guess, I want to quickly run through a bunch of other systems that people have tried to, in many cases, succeeded in building small quantum computers with. And I'm not going to say very much about each of them. I'm just going to kind of give you a sense of what's out there and what the different options are for building quantum computers. So one fairly important alternative to this whole approach is optical lattices. So optical lattices, well, suppose you take 2 lasers and shine them at each other, right? You get a standing wave. 2 lasers of the same frequency. You get a standing wave. So there'll be some places where the field is high and some places where the field is low. I mean, the high places field is oscillating, obviously, but the electric and magnetic fields are out of phase, so one of them will always be high. And if you take an atom has some energy levels which are kind of in resonance with this laser frequency, it will want to sit at certain places. You have the standing wave, so you have some places where it's high and some places where it's low, and they're evenly spaced. Okay? And you can make actually, you do it in one direction, you get a periodic thing in this way. You do it this direction also, and this direction also. Then you'll get a 3D lattice of points where it's high and low. And you put neutral atoms in that are just at the right frequency and will have an energy splitting at the right frequency. And they'll want to sit, I never remember which it is, maybe at the low points. OK? And so under the right conditions, you can take one of these optical lattices make a Bose-Einstein condensate of atoms, and feed it into the optical lattice, and the atoms will distribute themselves very evenly. And you can do some manipulation to make it even more even. So you'll have a nice lattice of atoms, 1 atom per site. Okay? And then by fiddling with the lasers, you can move the atoms in a state-dependent way. So the ground state of the atom will move separately from the excited state. And you can bring them in for controlled collisions with other atoms and stuff like that. And so you can get them to interact. So people, I mean, this started out as an idea for quantum computing, but it's now this big field of cold atoms that I mentioned before, where people take these things and they try to simulate all sorts of different Hamiltonians with them. So the advantage of this is that you can easily have many, many, many atoms, thousands, or I don't even know what the numbers are. The disadvantage is that it's hard, although people have managed it by now, to control individual atoms. Really what you're doing is something global. That's the easy thing. And so you can kind of make some global translational invariant Hamiltonian and simulate what's going on with that. But it's hard to do kind of a real computation in the sense that we've been talking about, where you do one gate, quantum gate, and then a different quantum gate. You can, there are tricks. You can convert even this kind of global control into a quantum circuit, but there's a lot of overhead in that. OK? So another option is linear optics. So in this case, the qubits are going to be individual photons. Say you could have a photon here or here, have two different spatial modes. And that's your 0 and your 1. And you can sort of, I mean, you can't really interact different photons with linear optics, but you can interact different modes by using beam splitters and phase shifters and all that stuff. And that lets you do a wide variety of gates on these atoms. But what's surprising is that you can actually do a universal set if you throw in photon counting detectors, or really single photon detectors in general. Okay? And the reason is that single photon detectors actually are nonlinear. There's a nonlinear aspect of them. And that lets you kind of do universal computation with linear optics. And there's a whole set of tricks that are associated with that, which are totally different from what I've been telling you about so far. So I'm not going to go into them. But this is another option for building quantum computers. So the advantages of it are that photons are very easy to find. It's hard to make just one photon when you want it. And it's also hard, of course, to keep photons in your computer. They tend to fly around. The speeds will be very fast, of course, because photons move around very quickly. But the other hard thing is to get them to interact, which is why you need these other tricks. But one advantage, again, is that you can do long-range gates very easily. Oh, I guess I didn't comment on that specifically in the superconductors. So the superconductors, because you want to wire them together to interact them, is a very strong preference to have gates between qubits that are close together. Because if you have to kind of get wires that are going all the way across the computer, then that becomes a real nightmare. You probably need to go into a third dimension to move them past each other and stuff like that. OK. Yeah. So another option is nuclear magnetic resonance. So in this case, your quantum computer is kind of like one molecule. And your qubits are nuclear spins in this molecule. OK? And adjacent nuclear spins have some kind of interaction through the electrons in the atoms. And that lets you do your 2-qubit gates connecting these spins. Now, there's various problems with this. So one is, first of all, that this coupling is always on. You definitely can't get rid of it. There's none of these tricks of cutting something off or tuning something in and out. It's always on. But the thing is, you also have a good single qubit control by because each of these atoms has a slightly different frequency. Each of these nuclei has a slightly different frequency due to different chemical environments. And that's the property that lets you use NMR for imaging, because you can see exactly what molecules are where based on kind of what frequencies you see. But it also means that by shining the appropriate microwave pulses on them, you can selectively manipulate the individual atoms. And once you have individual control of the single qubit gates, you can manage with a kind of an always-on 2-qubit gate by doing something that causes that to cancel out. Again, I don't have time to go into the details of that. The other big problem with NMR, well, there's a number of problems. First of all, because you're dealing with a molecule, you have to pick just the right molecule, and then scaling up to many, many molecules, many, many qubits is going to be hard. You would need a very big molecule, but that means you have an enormous number of separate frequencies to worry about of these different qubits, different atoms. Another problem is that you don't really have very good state preparation or measurement. Instead, you have kind of average collective stuff between the many molecules in your sample. And so that's an annoyance, but again, one that in principle can be dealt with. So NMR was kind of one of the first things that got quantum computers on the order of 10 qubits, because the technology is very well developed, but it's kind of stagnated and doesn't have a really long-term run, at least for liquid state NMR. OK, now I'm over time, but let me mention a few more things. So we have, let's start a new column. So we have NV centers. So diamond, of course, is a very regular crystal of carbon atoms. But you can have defects in that crystal. And in particular, if you have a nitrogen in one place instead of a carbon, well, carbon has 4 electrons. Nitrogen, I guess nitrogen has 5. And so carbon will bond to 4 other carbons. Nitrogen will only bond to 3. And that means that next to the nitrogen, there should be a place where there's no atom. And so that's the NV center, N nitrogen, V vacancy. And it turns out that this place where you have the NV center has really good coherence properties. So again, this is kind of an NMR thing. The qubit is going to be, I guess, the nuclear spin of the nitrogen. And it's very well isolated from the environment. The dephasing time is like minutes, something really long. And you can control it using the same tricks of shining light on it. The problem is with this is that it's pretty hard to get a situation where you have to somehow manufacture a diamond that has 2 of these right next to each other if you want them to interact. And so this has emerged as kind of a leading candidate for quantum sensing applications, where maybe you want 1 or 2 qubits and you want very high sensitivity. But it's maybe not so great for building quantum computers. But it's still there, kind of out there as a possibility. So another option is spins in silicon. So I mentioned that one advantage of superconducting technology is that it takes advantage of solid-state techniques, manufacturing techniques. But of course, the whole computer industry does solid-state manufacturing specifically with silicon. So there's a whole lot of knowledge and ability to manipulate silicon. So that's the motivation for these next 2, actually. So this is the other kind of leading solid-state candidate, is something to do with silicon. And so there's 2 main approaches there. And so one of them is to have silicon electrodes and then to embed single atoms in there. I think usually they use phosphorus atoms. And then the nuclear spin of the phosphorus atom is your qubit. So you can use some sort of NMR techniques. But you can get them if you have this electrode here and this electrode here, each of them with 1 phosphorus in. By connecting them through some electrical wire, you can turn on and off the coupling between those 2 qubits. So that's pretty good. It turns out somehow, and I don't really know the issues, to be much more difficult in practice to make this work. I mean, I think it may be dependent a little bit on getting the phosphorus exactly where you want it. If it's a little bit off, then that's the source of decoherence. And I think measurement is hard in these, but I don't really know the details. Certainly, it was an exciting proposal when it was first made, but it has not advanced very far. And another one is quantum dots. So quantum dot is kind of a silicon well that will, sometimes they're called artificial atoms, and so you'll have some energy levels of electrons in this well, and that could be your ground and excited state if you have two, or you focus on two. And again, you can kind of put quantum dots next to each other and let electrons tunnel back and forth. That gives you an exchange interaction. You can make all sorts of things out of this. And so that's again, something that people are working on. I think getting the decoherence rates low enough to be competitive with these other approaches has been hard. And so that's the reason that one has not become a leader. OK, so there's actually all sorts of other implementations. These are kind of the ones that are maybe worth knowing something about. I didn't say anything about topological qubits. That's a whole other area, but it kind of requires way too much additional machinery to talk about. So I'll leave it there for today. Are there questions? OK, so next week, we're going to change topics again. We're going to start talking about quantum complexity, classical and quantum complexity, and quantum algorithms.